want to thank everybody for taking time today to join today's webinar. My name is Kevin Davis. I'm a technical consulting engineer working in the Developer Products Division at Intel. And as Mike indicated, our webinar topic today is an introduction to Intel Visual Fortran development for the Intel Xeon Phi coprocessor. We're going to be taking a look at several areas today. We'll take a look at some system requirements and installation details, programming models specific to the Xeon Phi coprocessor, using the Intel Fortran compiler, language extensions for one particular programming model known as offload, and then some environment controls and some reports related to that offload model implementation. So the support for the Intel Xeon Phi coprocessor on Windows was introduced in the Intel Visual Fortran Composer XE 2013 Service Pack 1 release. And in this webinar, I'm going to introduce you to the development environment for developing Fortran Windows-based apps that target the Xeon Phi coprocessor. And my objective is to demonstrate to you that programming for the Xeon Phi really is a simple extension of programming for your CPU host. We'll start with some system requirements and installation details. First, some basic hardware system requirements. I've only listed a few on the foil here that are necessary to support the Xeon Phi coprocessor. You should refer to the Xeon Phi technical documents for more information and all of the system requirements that are necessary. Those are available from at the URL that I've noted on the foil. The article that I've cited at the bottom also contains a where to buy guide link that you can visit and obtain a list of our partners from whom you can purchase Xeon-based systems with the Xeon Phi coprocessors installed. In terms of our basic software requirements for development on Windows, there's 4 basic requirements that I've noted here on the foil. We're going to talk about specific versions of these and some of the details on the next few foils. We're going to start talking about the Intel Multi-Core Platform Software Stack. This is commonly referred to as MPSS. So for development on Windows targeting the Xeon Phi coprocessor, on your Xeon Phi system, you'll want to install both of the components of MPSS. There's the MPSS coprocessor component and the MPSS Essentials component. Now, the coprocessor component contains all of the system-level drivers, utilities and libraries, as well as the Linux OS image that is loaded and runs on the coprocessor itself. And the MPSS Essentials package contains all of the necessary development tools for targeting apps to run on the Xeon Phi coprocessor. Now, if your development environment contains other development systems besides your Xeon Phi, you can develop for Xeon Phi on those systems. You would need to meet the requirement of having the Visual Fortran and the Microsoft Visual Studio, and then this MPSS Essentials package is all that would be required on those hosts. In terms of the Microsoft Windows 64-bit operating systems, the versions that are validated and supported for the Xeon Phi coprocessor are listed here on the foil. There's 2 enterprise versions and 2 server versions. The article that I've cited at the bottom of this foil is an IDZ article that's kept up to date with the latest information regarding MPSS. So I would recommend perhaps bookmarking that or even subscribing to that article so that you can stay informed about the latest versions of MPSS that are available. A little bit more about the Visual Fortran component. What we recommend for development on Windows targeting the Xeon Phi coprocessor is, as I mentioned, at least our Service Pack 1 release or higher. And then we recommend a minimum Visual Studio version of 2012 Professional Edition, and I'll talk more about that in just a moment. The Visual Fortran component itself does support earlier versions than 2012, but we'll talk about that on the next foil. In terms of application deployment on Windows, if you have added support for the Xeon Phi coprocessor and you develop applications that currently use our redistributable package, there's nothing that changes with respect to that. The redistributable package for Visual Fortran, beginning with the Service Pack 1, will contain the necessary support for the Xeon Phi as well. The article or the URL I've noted here with respect to the redistributable packages contains links to download those as well as other information. And if you're perhaps new or might not know about our Visual Fortran product and what features it does provide, you can visit the URL at the bottom for more information about the compilers and other packages that it's available in. Next, I wanted to talk about some of the installation specifics. I characterize MPSS and the Visual Fortran products as development dependent, but installation and upgrade independent. The Visual Fortran Composer, when you are targeting the Xeon Phi support, does depend on that MPSS Essentials package that I described a couple foils back. So that's the development dependency specific to Xeon Phi. Now, the two components can be installed and upgraded independent of one another. There is some aspects of the Visual Fortran installation that are aware of MPSS, but there is no dependency in terms of the installation or the upgrade of either one. In terms of installed versions, if you're an existing Visual Fortran user, you might know that the product does support having multiple versions installed side by side on a single host. But MPSS is limited to only a single version installed on the Xeon Phi system. With the installation of the Visual Fortran product, our Xeon Phi components will install with our Intel 64 components. And then there are some Intel debugger extensions specific to supporting the Intel Mic architecture or the Xeon Phi coprocessor that will install if you've met this minimum Visual Studio requirement that I mentioned earlier, the version 2012. So during the installation, if you do not or are unable to meet the minimum requirement, the Intel Mic architecture debug extensions will not be installed, but you will receive a notification at installation time as shown in the graphic here. So the impact of not having these debugger extensions is only on the ability to debug Xeon Phi specific code. So you would have to use some alternative debug methods in the absence of these debugger extensions. Now, the debugging of the host code is unaffected by the absence of these, as well as you can also develop still and target for the Xeon Phi with earlier versions of Visual Studio. So the Fortran Composer package supports as far back as Visual Studio 2008. All right. The last bit of information I wanted to share about the installation is just the installation summary. Again, just repeating what I mentioned earlier, the Xeon Phi components for the compiler are bundled and installed with the Intel 64 components. You still may, if you are developing for IE32, you can still install the IE32 development environment and develop applications for that platform. Now, the MKL Xeon Phi support, if you're interested, does have a separate selectable ability to install or not install the Xeon Phi specific support. And then, as I've sort of highlighted on this installation summary screen, when you do meet the minimum requirement for Visual Studio for the Intel Mic architecture debug extensions, those will be installed, and you get an indication that those are being installed. That's all I had in terms of system requirements and installation. And the next thing I wanted to talk about were programming models. With the introduction of the Xeon Phi, you have sort of a range of program models that become available. They range from a multi-core centric set of models to the many-core centric models. We're going to start on the left side of our range and talk first about the multi-core hosted model. This is a model where you have general purpose serial code in the application combined with parallel computing, where you would spread your parallel computing across the multiple cores of the host CPU. And to the lower portion of the foil, we're depicting in the yellow box here for this model where the code would execute. So it's exclusive to the multi-core host. The next model is one known as offload. Now, this is a combination of multi-core hosted code where you also take the highly parallel phases and you offload or you execute those on your many-core coprocessor. Then moving further to the right on the range, there's another model known as symmetric. This is a model where you take the code's needs and you balance that across your multi-core processor as well as the many-core coprocessor. Now, this model is not available for Windows with the Xeon Phi coprocessor. So we move further to the right to our many-core centric models. We have our many-core hosted model. This is a model where you take highly parallel codes and you build them to run exclusively on the many-core coprocessor. This is available for Windows, with the Xeon Phi coprocessor, but in the absence of support for MPI. Most of our discussions for the webinar today are going to focus on the offload model from this point on. So the offload programming model, sometimes referred to as the heterogeneous programming model, is one where the programmer would designate code sections that would run on the Xeon Phi coprocessor. This is an explicit data sharing model between the host CPU and the target, or the coprocessor. Now the compiler in the runtime is responsible for and automatically takes care of managing the setup and the teardown and the remote execution of the offloaded code, as well as any data transfers and synchronizations that are necessary or associated with that code. And what it does, the compiler in runtime will emulate a sharing of data between the host CPU and the target by copying values for variables that are used or within the offloaded code back and forth at the points of offload. With the offloading model, there are two types of behavior. There's what we call a mandatory or an optional behavior. With the mandatory behavior, in the absence of a coprocessor, at the point of the initial offload, if there is in the absence of a coprocessor, the program would halt with an error. The opposite of that, it would be the optional model, where you would build the application such that in the absence of the coprocessor, the application can continue to run entirely on the host CPU. So I'm going to talk next a little bit about the specifics of some offload compilation, and this is getting more into the specifics of the Intel implementation of this particular model within our Fortran compiler. So we've created what I sort of characterize as a unified host and target compilation. This is automatically done. There's no action that the user needs to take, and the compiler performs this unified compilation both under the command line as well as the Microsoft Visual Studio environment. The user interacts with the compiler from the host perspective of the compilation, but we do have support in the form of a compiler option as well as Microsoft Visual Studio property settings to independently control the target compilation and provide separate options to that. A part of the unified compilation are merged compilation diagnostics from these two compilations that occur. And within the Intel implementation, we have tagged our target-specific diagnostics with a unique string star might star, so that those are distinguishable from the intermixing that can occur. The simple graphic at the bottom just is a simple representation of the compilation. From a user's perspective, you provide the source files to the compilation. And one thing that is unique is we produce what's termed a unified executable. So you have a Windows host portion of an executable, which is shaded in the sort of the green tone here, and then you have another yellow portion, which is actually the target executable, and it is physically merged into one single .xeon disk. And we'll talk a little bit more about that because it's more than just the exe that's merged. Within the offload compilation and this unified compilation that occurs, the host and target compilations do in fact generate unique object files. But with the objects and the executable, the Intel compiler and other associated tools unify the object files into a single .obj on disk, as well as a single .exe. Now, currently in the Service Pack 1 release, this is only occurring for objects and executables. If you do build DLLs or static libraries as a part of your application for Windows, in the current release you will see some separate object files and separate lib files. We'll talk a little bit more about that as well later, but these are also merged in our future release due out later this year. So you will see just a single .dll or a single .lib depending upon what you're building. Again, the Intel tools and the compiler are all customized to support these unified object files. There is a user utility that is shipped with the compiler. It's typically used from a debug perspective, but you can use the utility to extract those host components if you need to. For host files, those are really unchanged in terms of the host files for the for the mod files for the host. I think I just confused myself. What I meant to say is the mod files are unchanged in terms of the host, and we've introduced the new mod files for the target. So if you have modules in your application today, you're familiar with the .mod file that is created. Those are unchanged for the host. And then any source file containing modules that participates in the target compilation will generate a new file called .modmic. Now, these are specific only to the target compilation, but you might see those if you have source files with modules participating in that target compilation. Lastly, what I wanted to talk about in terms of the offload model is just a simple sort of flow of the execution. On the graphic we have here, on the left side of the graphic, it represents our host image or our host source code, and we've added the necessary directives which define the target image, which you see in the center of the foil. And in terms of the execution would begin on the host at the first point of offload. Let's assume for discussion here that it's within our subroutine F, and the assignment to A is what's been offloaded. At the first point of offload, the runtime will check for the availability of the coprocessor, and under that mandatory behavior that I described, if the coprocessor is unavailable, the program would abort at this point. Now, under the optional behavior, in the absence of the coprocessor, the execution at this point would just simply remain entirely on the host until the host executable was complete. With the coprocessor available, the runtime will acquire the coprocessor and then load the target image and then execute the associated offloaded code. In this case, it's the assignment to A, which also includes the execution of function G. At the end of the offloaded code, the execution would transfer back to the host image at the point of offload, and this would be within our subroutine F and at the call to the subprogram, our subroutine H. So if there were any other points of offload within the host application, they would simply use the coprocessor and execute the associated offload code in the target image and then return control similarly. So at the end of the host program termination, the target program would be unloaded and the coprocessor would be released. So that's a simplified explanation of how the offload execution works, and that's really all I had in terms of the offload programming model specific to the Xeon Phi. Next, what I wanted to talk about were the specifics of actually using the compiler and calling out the support specific to Xeon Phi. Now, first, we're going to take a look at using the compiler from the command line. And really, with the addition of Xeon Phi support, with the exception of some additional compiler options, the use from the command line is really unchanged. The installation will still create a folder of shortcuts that open command prompt windows that are pre-initialized for using the compiler from the command line. If you aren't familiar with that, you can refer to the user's guide for a nice section about how to use the compiler from the command line. But from the command line, the compiler can be used in 3 usage modes. There's what I characterize as CPU only. This is where you would build CPU or executables that would run exclusively on the host CPU. Now, if you happen to have offload directives in the code, you can disable those with the qoffload none option that's shown on the foil. And that would, again, build an executable that would run exclusively on the host CPU. By default, from the command line, the compiler behaves or operates in this heterogeneous compilation mode that I just described. So it will recognize offload directives and generate the CPU as well as the target images. The one other mode that's available for the compiler under the command line is the native mode, and this is used with the /q mic option. I do want to talk a little bit more about this. Along with the -q mic option, the other compiler options that you provide to the compiler must use the Linux-style hyphenated form of the option. So if you don't know the Linux form, they're very easily found within our user's guide. Our user's guide, the compiler options are documented, and on a single, under the documentation for a single option, we include all the spellings for the OS versions that we support. So if you know the Windows version of the option, go into the user's guide looking for that, and you will find the Linux style. One other thing to note about native mode is that currently, with the current implementation, you can only build native applications targeting the Xeon Phi coprocessor from the command line. We will be looking at whether or not we can support building native under the Visual Studio environment in a future release, but at present, you may only use the command line interface. Debugging, as we've described earlier, let's assume that you have met the minimum Visual Studio requirement, for debugging native applications, you would only be able to do that under the Microsoft Visual Studio environment, and you would use the method of attaching to the process that's actually running on the coprocessor. And just a couple of other points to sort of complete the picture in terms of native mode. You build the application, you transfer the executable or library and any other runtime libraries that it requires to the coprocessor, and then you'd establish a virtual terminal connection to the coprocessor to then interact and run the application directly on the coprocessor. Okay, next I want to talk about using the compiler under the Microsoft Visual Studio environment. Again, the introduction of the support for the Xeon Phi really has changed little with respect to the existing integrations if you're familiar with using the compiler under the Visual Studio environment. We have a few unique offload model specific property settings. And then, as I've mentioned earlier, we have the unique Intel Mic Architecture debugger extensions. If you're not familiar with using the compiler under the Visual Studio environment, we have a nice section in the user's guide that's noted here on the foil. Now, with respect to the offload programming model, this is supported only with the x64 platform type. And unfortunately, under our current implementation with the Service Pack 1 release, we do have some problematic handling that can occur. And this only occurs for solutions where you have both the Win32 and the x64 platform types, and you've added some support to use the offload model within your source code, and that source code is visible to the Win32 platform type at build time. If you sort of fit all of those requirements, what you would want to do temporarily for the Win32 platform type is just disable the recognition of those offload directives. One of the things you're seeing here, and we'll talk a little bit about it more in the next section, is that there are actually two offload implementations that the Intel compiler supports. There's the Intel implementation, which you would disable for this Win32 situation with the QOffload none, and then there's the OpenMP implementation, which you would disable with the QOpenMP -offload minus. I want to take a little bit closer look at the actual property settings. Now, this is specific to the Intel implementation of the offload model. These property settings will only be visible when you're under your x64 platform type, so they're not visible to the Win32 platform. Let's see. So the Intel offload directives, you can control the behavior or recognition of those using a new property setting that's under the Fortran code generation collection. It's known as offload constructs. The default for the Intel offload directives is this mandatory behavior that I've described earlier. I also mentioned earlier the ability to control that target compilation, and you can do that under the Visual Studio environment through the additional options for Mic Offload Compiler property setting. One other related option for controlling the target link is under the linker general collection, and that's the additional options for the Mic Offload linker. Okay. So specific to the OpenMP implementation of the offload model and the target constructs, this is not a new property setting, but it's the one that controls the recognition of the OpenMP directives, which includes the target and the SIMD constructs from the OpenMP implementation, the 4.0 implementation. But under Fortran language, you can disable or enable the recognition of OpenMP directives from the process OpenMP directives property setting. And then to control either the target construct directives and their behavior or recognition, or the SIMD constructs, you'd need to do that utilizing the property setting for Fortran command line additional options. By default, when you enable recognition of the OpenMP directives using the property setting mentioned in the first bullet, you then have control over the target or the SIMD from the additional options using the compiler options that are shown. By default, those options are recognized and processed. Okay, I'm going to talk a little bit more about the debugging specific to Xeon Phi under the Visual Studio environment. Let's see, it does require MPSS 3.1 or later. It does require the Service Pack 1 release that we've talked about. This is where the debug extensions and the support for Xeon Phi was introduced. we have full integration of debugging of Xeon Phi into the Microsoft Visual Studio, so there is no command line debugger available for Xeon Phi debugging. We've talked about the minimum requirement for Visual Studio 2012. If you are a user that's using Visual Studio 2013, you will want to get our Update 1 to Service Pack 1. That's where we introduced support for Visual Studio 2013. And these debug extensions, they don't really impact the debugging of the host, but what you can do is you can debug on the host, you can debug offloaded code, and you can debug native Fortran applications. The article that I've cited at the bottom of the page has some more complete information of debugging specific to Xeon Phi into the Visual Studio environment. The next few foils are some screen snaps, and I wanted to just give you a sense of the level of integration for debugging of an offloaded application under the Visual Studio environment. The first screen snap here is just showing some breakpoints. I have a breakpoint set at line 124, which is within host code. The other is a breakpoint that appears within an offloaded region that's at line 145. So it's in the middle of a loop that I've designated as a candidate for offload using the offload directives. From the source view, you can see that there's the breakpoints are the same in terms of whether they appear within the host or offloaded code. And then below the source code, I've opened up the breakpoints view, and you can see that they're also all listed here, so we have an interleaving of all the breakpoints within a single view. There's no different treatment of them whether they appear in offloaded or host code. The next screen has lots of views that I've opened just to kind of give you a sense of all of the information that's available when you're debugging an application with offloaded code. In this first screen snap, I've stopped the execution at line 124, which is within our host executable. And what you can see in the process view below the source code is the actual processes that are active. So I am stopped within my host process, and what you see is also two offload main processes. So this debugging session was on a Windows system that had two Xeon Phi coprocessors installed, and the offloaded code executes on the coprocessors under this process offload main. So I had some offloaded regions that executed prior to reaching this breakpoint. And as you remember from our earlier discussion, we've acquired the target, the coprocessor, and we've loaded our target image. And that's the reflection of what the offload main is reflecting, is the loading of the target image. We can see from in the middle, sort of the middle of the top view, we can see the main thread that's executing, and then in the detailed process thread view, we can associate that with the process and see the actual thread that's running. And then in the lower right corner of the screen, the process call stack reflects that of the host process. So if I were to continue execution down to the breakpoint within the loop, within the offloaded code, the view really changes minimally. What you can tell from the changes in the view is the process, in the process view below the source code, we can now see that the execution is stopped within one of my offload mains. In the top center of the screen, we can see the offload thread that was in execution at the time of reaching the breakpoint. And in the process thread view, we can associate the process and the thread that's in execution. And while it may be new to some of you today, the process call stack is reflective of the actual offload process. The dot out in the process call stack is reflective of the target image. So you can see from just these few screen snaps just how seamlessly the debugging has been integrated into the Microsoft Visual Studio environment for debugging not only host but offloaded code. There are a couple of other screen snaps that I did want to show you today. There is something that can occur when you are initiating some debugging of the offloaded code, and the debugger is attempting to make the connection to these offload processes. It's just a premature stoppage that would occur unexpectedly. You can see from the view in the process panel that we are stopped within an offload process. What you want to do if you do experience this is you just want to continue execution until you hit a user-defined breakpoint. It is something that can occur, again, when just we're trying to launch the debugger and attach to these offload processes after the target image has been loaded. Another sort of variant of this same condition that can occur might look like this, where you get a code not running type of an indication. Again, take a look at the process that's running to sort of get a feel for where you're at. You can also see to the bottom right the call stack is reflective of the offload process as well. That's all I wanted to talk about today in terms of using the compiler. Then next, what I wanted to really look at were the Fortran-specific language extensions that support the offload programming model and what the Intel compiler supports. As I hinted to in the last section, the Intel Fortran compiler does support two offload implementations. We have the Intel proprietary implementation, which is based on the offload directives. We'll take a quick look at some of the directives, but we won't go into detail today, just to want to stay within the time constraints that we have. But if you are not familiar with those, they are documented in the user's guide in the sections that's noted here in the foil. The other implementation that the Fortran compiler supports is the OpenMP 4.0 API specification. The offload support specifically is tied to the target construct directive. The SIMD construct directives I'm just mentioning here because we do support those and they are part of the OpenMP 4.0 API. Now, we also document the target construct and SIMD directives in our user's guide, but you can also obtain the complete specifications from OpenMP at the URL that's noted on the foil. And as you'll see, as we go through the next few foils, there are some unique directives to each of these implementations. We saw from previous sections there's some unique compiler options, but the two implementations actually share a common underlying runtime support. So next we'll take a look at some of the directives. This is for the Intel implementation, the offload directives. There's three main directives under this implementation. The three main directives for designating offloading of structured blocks or statements. We have the OMP offload directive, which is designed to offload an OpenMP structured block. We have the offload directive that offloads a single statement, which can include subprogram calls, can be a simple assignment statement, or as in our example we saw earlier, we had a simple assignment statement with a function call. And then we have the offload begin and end offload directive pair that's used to designate a structured block to be offloaded. One of the things that also exists is an extension to the attributes directive. It's the offload keyword. If you might have seen that from the previous example, and this is the directive that you would use to declare subprograms and variables for being a part of the target image. Let's see, I want to go back here real quick. One of the other things I wanted to mention about the directives is there are a set of clauses, and some of the clauses have a set of modifiers, and we'll take a quick look at those clauses as well. But there's two other variants on the offload directives. There's an offload transfer, which is a directive for either initiating synchronous or asynchronous data transfers only. There's no executable code associated with that directive. And then there's the offload wait directive that you can use for synchronization with previously initiated asynchronous activities. One of the clauses that you can use, and we'll see it coming up, can be used with these directives as well as the earlier directives, and that's to create asynchronous offload activities. Some of the clauses that are available, they range from clauses that allow you to control selection of coprocessors to assigning other conditions to the offload. These can be programmatic conditions to determine whether an offload would occur. And then moving down, there's the data input-output type directives or clauses that are used for tailoring the data transfers that are associated with the offloaded code. And data transfer or the data inputs and outputs are the clauses that have some additional modifiers. These are some of the additional clauses that I mentioned can be used with controlling synchronous or asynchronous activities. Some of the modifiers that go along with the tailoring of the data clauses are listed here on the foil. These can do anything from specifying number of elements to copy to dealing or handling the allocation and freeing of memory on the device associated with data transfers and variables that you transfer into the offloaded code. Real quickly, the OpenMP 4.0 device constructs that we support, or that are from the specification. There is the target in-target directive pair, which is used for offloading a structured block. They have the target update and the target data in-target data pair, which are for manipulation of the data environment on the target device. And then they have, similar to the attributes offload that I described, they have the declare target directive, and this is under the OpenMP 4.0 implementation, what you would use to then map subprograms or variables to the target device. Similar to the Intel implementation, the OpenMP 4.0 has a set of clauses that are used with the directives. Some of them look very similar. They have a clause for controlling or selecting the device, assigning additional conditions to whether the code would offload or execute on the device. And then their main data input output is the map directive, and there's specific map types available with that clause for controlling or tailoring the data transfers associated with the data environment that you create on the device. And here's the map type controls. I know that was kind of fast. That's really all the time we have. I just wanted to give you a feel for the look of the directives from both of those implementations. Some other specifics about the offload data and the transfers associated with the offloaded code. There are some limitations in terms of the data types that can be used with the offloaded code. They are limited to scalars and arrays and bitwise copyable derived types. The current implementation of the Service Pack 1 release does not support derived types with an allocatable component. But the release due out later this year will support the allocatable component. The limitation does exclude most of the Fortran 2003 object constructs. Now, with those limitations, though, the data that's exclusive to the coprocessor, so data that you use within your offloaded code, has no restrictions in terms of the complexity. It's just the data that is transferred. Now, by default, there are there's some default transfers that the compiler does perform with respect to the data transfers. Any scalars or named arrays that appear within the lexical scope of your designated offloaded structured block, by default, those values will be copied in at the beginning of the offload and out at the end of the offload. And this applies to both of the implementations that I mentioned. So you want to take a look at the data transfers, and you can tailor those with some of those clauses that I described earlier under both of the implementations, and minimize the amount of data transfer that's necessary for the offloaded code. There's some data also that's not automatically transferred, and that would be memory that's pointed to by pointers, or any global variables that might be used down to subprogram calls that originate from offloaded code that the compiler can't not see down that call chain. In terms of offloading, the offload program models and using Windows-specific features, you may not use any Windows-specific OS features within your offloaded code. And any attempt to do that would result in some errors or perhaps some other lesser diagnostics for any attempt to use those inside the offloaded code. And there's also a case where just the appearance of Windows-specific features within your source code that participates in the target compilation, those can also trigger diagnostics, and I'll show an example of that a little bit later. So when you begin to consider programming for the offload model, you may have to do some code restructuring to try and prevent any Windows-specific features from being visible during that target compilation. And the list of Windows features here on the foil are just a few, just to give you an example of those types of Windows features that are not supported. This is not the exhaustive list. You can refer to the documentation for a bit more description of what the limitations are. There are a couple of preprocessor defines that the compiler does define related to the offload programming models. There's the _Intel_offload. This is defined both during the compilation of the host as well as the target compilation. You might use this to protect calls. The example here in the foil is a call that you want to protect and only execute on the host side. The other define that is created is a double underscore mic, double underscore. This is defined only during the target compilation. And the example here is that you might use this to protect code that's only intended for execution on the coprocessor. Next, I want to talk about building static and dynamic libraries that contain offloaded code. I mentioned these earlier. Now, there's really nearly no special action required from the developer. In terms of this, you would add your offload directive, build and use the library. And it sounds pretty simple, and it really is. We've taken with the compiler and the XI tools, the XIAR and XILib, we've seamlessly integrated those with lib and link to handle these host and target object files that I described earlier, and create the necessary Windows host library and Linux sister library, whether you're building a static library or whether you're building a DLL. In the case of building a static library, what you would see on disk would be a .lib for the Windows library or a .a for the Linux static archive. For DLLs, you'll see the .dll or a .out, which is the distributed shared object for the Linux target library. From a programming standpoint, you still only make reference to the host version of the library. The compiler and the XI tools will take and invisibly handle promotion of the library to the target link as necessary. If you happen to have a solution, for example, where you have an executable that depends on a Windows static library, and you've added offloaded code to your static library, and you have the solution and project dependencies set up under Visual Studio, where the executable automatically links with the static library as per the dependency you've established, that's unaffected when you add the offloaded code. You do nothing more. Now, if you're building a DLL and you do any handling of that DLL after it's built, for the current release, you'll want to make note that you will have to also handle the .out file. Now, you only have to handle it in the sense that if you, for example, copy your DLL to perhaps place it next to an executable for convenience, you'll want to make sure you copy the .out. When at execution time, when you enter the DLL and go to execute your offloaded code, the compiler runtime will handle the loading of the .out target image. So you don't have to do anything other than just making sure that those two, for the current release, are sort of copied and handled together, or distributed if you're doing a distribution of a DLL. As I mentioned earlier, in the next release due out later this year, we have unification of the objects as well as these libraries, so you will only see the .lib on disk and the .dll, so the handling becomes much more simplified in the release later this year. A couple of other points I wanted to make about building dynamic link libraries that contain offloaded code. There is another requirement today where you have to provide the -fpic to the target compilation, and this is just a necessary step to ensure that the dynamic shared library is built with the necessary position-independent code. So if you're building under the IDE, you'll want to add the option to the additional options for the mic offload compiler that we mentioned earlier. And from the command line, you can use the Q offload option with its other required arguments of the target, which is mic, and the tool, which is compiler, and then the option. One last word about libraries with offloaded code. I mentioned earlier about having Windows OS-specific features visible to the target compilation. I had an example where I was building a DLL, and I had used the attributes DLL export directive to export my entry point. In the absence of the #if ndef that you see here, you would receive the remark shown in the blue highlight during the target compilation. So you can quiescent that with using, I just happened to use the _mic, _define, and was able to quiescent the remark. One last note, important note, if you are building a DLL and linking that to a main program that does not have any offloaded code within it, you will need to go ahead and link that main program with the Q offload option. This makes sure that we have some linkage to the offload runtime in order to support the offloaded code within your dynamic link library. Well, the final thing I wanted to mention, I don't know what that is. Do I know how to deal with that, Mike? Screen sharing is paused. I'm not sure what happened here.
Yeah, I'm not sure. Maybe your system froze up a little. Can you go back or forward?
Here you go. This is the foil I was hoping to talk about. It says move this window away from the shared application.
Yeah, I'm not sure what's happened. Are you able to? We don't see a new foil yet.
Okay, you're still on which foil?
The building libraries. Building
Okay.
libraries with offload code. You can just.
I'm sorry, I don't know.
Okay.
What's
you can just talk.
Here. Okay. Maybe it's coming back now.
There we go. Offload APIs.
Okay. All right, so offloading, I apologize for the technical hiccup there. The last thing I wanted to mention about the offload implementation is some new module that is distributed with the compiler. It's called the mic_lib module, and this contains APIs that are specific to the offload implementation. Contains things that APIs that allow you to query things about the coprocessor, perhaps the number of them that are available. If you are an OpenMP user and you are using OpenMP within your target code, this might be a neat set of APIs. You can actually control the target API, target OpenMP configuration from the host using these APIs. And there's many more. I just listed a few here on the foil. The source is available with the compiler, but it does come pre-compiled. So you just simply add a use mic lib wherever you'd like to use these APIs. Let's see if I can. Okay, I'm not sure. It's not advancing for me now. Okay. Oh, it looks like it's frozen up on me. I guess what I'll talk to, and I don't know if the foils will come up at some point. The last section was just about some environment variable controls that exist specific to the offload application or the offload programming models, as well as a couple of reports that are available. There's a set of environment variables that you can set to control the use of the coprocessor from an environment variable perspective. So you don't have to make modifications to your application. For some of these, you can just control the use. You can limit the coprocessors that you use. You can establish some stack-based settings for your OpenMP code. And you can also enable some reporting. There's an offload report variable that you can set to control getting a runtime report with respect to the offload implementation that you've added to your code. So I wish I could get my foils up here. Let's see, there is an offload report that you can get at compile time. There's a particular option. It's Q opt report phase : offload. And this is a static analysis of the offload directives that you've added to your code, and it gives you an indication of the it gives you an indication of the directives that were processed, and then some information about static information about variable transfers that have occurred in association with that offloaded code. The other report that's available is a runtime report where you can, there's 3 levels to the offload runtime report, the 1, 2, or 3. The highest level will give you indications of the offload sections that have executed. It gives you a source line correlation and gives you information about the variables that were transferred, whether they were transferred in or out or just out. And then it gives you information on the amount of data transfer that occurred, as well as some timing. They have some timing with respect to the CPU time of the entire offload application or the entire offload execution, and then some time for the actual offloaded code itself. There were a couple of other things that I wanted to show in terms of graphics. Let me see if I can. Can't get the foils to advance. I wanted to show you the Intel Xeon Phi coprocessor developer site. If you aren't already familiar with this, there's a developer site where you can get a lot of information with respect to the architecture. There's programming resources available there. There's self-guided training. We have case studies also that are available, as well as some blogs and other articles. And then lastly, I wanted to leave you with some information, and you can't see it, but it's about some coprocessor starter kits. You can get to this if you can find the Intel Xeon Phi developer site, but there are some coprocessor starter kits that are available. They come in a server or a desktop form. Coprocessor is included. The software is included, as well as 2 other textbooks. There's a textbook devoted to the Xeon Phi itself, and then another that's devoted to parallel programming. And so that's all I had in terms of my prepared material. I apologize. I don't know why the presentation sort of froze up here. I did want to thank Mike for his help today, and also my colleagues Ron Green and Steve Lionel for being online and helping answer questions. So Mike, I guess in the time we have remaining, we could take a few questions if there were any that came in.
We have a couple of questions, and we do have some time if anyone else would like to send in any other questions. In the meantime, maybe, Kevin, you're able to get your screen advanced somehow to your other slides. We'll see if that can happen during the Q&A portion. Again, if you send in questions, we don't have time to get to all of them. I'll make sure that they get in front of Kevin and he can answer you offline. So the first question asks, can I develop mixed language applications that use offload code?
Okay, the answer is yes, you can. Now, if you, for example, if you are developing mixed language applications with Microsoft, say, C and Intel Fortran, your offloaded code would be limited to just your Fortran. And trying to get things going here. But if you happen to use the Intel C compiler with the Xeon Phi support, you could actually do mixed language development that includes your offloaded code as well. So you could have Fortran calling C within the target image or vice versa. So mixed language programming is possible with offloading.
And we had another question that came in that asked about a recording of this webinar. Yes, we are recording this. It will be available at a later time. I'll send emails to everyone, letting them know that when this is ready, we'll get a copy of Kevin's presentation, put in a PDF form along with it, so that you can download it and have this material available to you at a later time. Again, hopefully within the next week or so, we'll be able to get that online for everyone. Next question asks, what is the behavior of the debugger when debugging offload code under the Microsoft Visual Studio 2010 when the Xeon Phi debugger extensions are not installed?
Okay. So if we can assume we've established a breakpoint within our offloaded code in the absence of the debugger extensions. I haven't actually tried this myself, but so with your offloaded code, you have a host image and you have a target image. What I envision would probably happen in the absence of the Intel Mike architecture debug extensions is you could set the breakpoint, and it would appear set, but the execution, if it did offload, it would not see that breakpoint. But if you didn't offload and you executed that code segment on the host, then that breakpoint should be seen